tell us to submit a paper. So we didn't get a publication, but we did get the patent. We were trying to keep it a secret. At the time, TI paid $1 in other considerations for a patent. Namely, the other considerations were you're continuing to draw a paycheck. After the Device Research Conference blew our cover that gallium arsenide does emit light, we rushed to market with the SNX 100 gallium arsenide LED, $130 a piece. We got a telex. This man wanted 100 units. Wow, first big sale. We shipped 50 that day and back ordered the next 50 to ship in a week. The day we shipped the second 50, we got 49 of the first 50 back, said that was a typo, we wanted one. You know, we thought it was so. We impressed him we could deliver. We didn't make the big sale. These were a little steep in price to find widespread application, but they did begin to open up the field of optoelectronics. Now we used the same zinc diffusion here that had been used in the Bractor in the solar cell. We used the tin alloy from the tunnel diode for the N-type contact, and Gary did that by plating molybdenum wires with tin and laying them on the top of the device and heating them up on a strip heater and alloying them in. It made an excellent N-type contact, but again, not a production process by today's standards. Now, TI had already entered the opto component business with a phototransistor detector in a pill pack that was used by IBM and others to read the holes in punch cards that were used to input data to computers at the time, digital computers. The light source they used was a standard lamp, a tungsten ribbon lamp made by General Electric with a fiber bundle that collected the light from the lamp and divided it up into 12 channels to read the holes in the punch cards. Now they liked the opto for reading the punch cards because it didn't wear the cards out. Prior to that they had held through the holes in the card with a wire, but after you ran the cards through the beater machine a number of times it would begin to tear the cards up. And the opto technique was a non-contacting way of reading the cards. So when we got the LED, we could replace the GE standard lamp with 12 LEDs and gave a lot more reliable system, a lot smaller, more compact, and a lot less power drain and heat generation than you had with that GE ribbon lamp. The optoelectronics industry was born. It was time for the LED to happen. The technology was there. TI and other companies had made large investment in material growth and purification. There were rudimentary techniques for ohmic contacts, diffusion. All those things were there. The technology was ready to support the development of the LED. Now the reliability problem that was that showed up in the tunnel diode also affected the LEDs. When you biased an LED in the forward direction at a constant current, the light output of the LED went down with time. Now, having had that reliability with the tunnel diode, we were alert to the possibility that gallium arsenide devices could degrade, so we did pretty extensive reliability testing, and we found the degradation in the LEDs before we introduced them into the marketplace. These diffuse junction LEDs degraded by dark line defects. The minority carriers in the device that recombine and emit light are the good ones. The ones that recombine non-radiatively on the dislocations in the material or at the surface provide extra energy to the lattice that allows these dislocations to propagate and migrate through the crystal and generate dark line defects. Now, these arc lines we discovered in 1964, published our findings in 1966 at a gallium arsenide conference in Reading, England. They were rediscovered at Bell Labs in the 70s, and fortunately for us, one of the reviewers of the Bell paper when they submitted it for publication remembered our earlier publication and saw to it that our paper was referenced. The dark line defects look like this on 111 material. They follow the 110 directions or perpendicular to the 110s, depending on whether they're moving by glide or climb. They're regions in which the diode is no longer drawing injection current and no light is being emitted. The regions between the dark lines are unchanged. If you plot light output against forward voltage, even when a diode is degraded where it's putting out a tenth of the light that it was at a given current at an earlier time, the light output at a given VF is the same. So it's a shunt current mechanism that when you run the diode at a constant current and the current in these dark lines builds up over time, the current left to bias the remainder of the diode goes down if the total current's a constant. So the degradation here doesn't change the material between the dark lines, but it does cause the diode to become more conductive and the light output to go down if you're driving it with a constant current. Now the dark spot in the center here was a flaw in the image converter tube that we used to take the picture. Someone had put a spot on it that was too bright and left it on it too long. This was an old World War II snooper scope that we converted. And that dark blob shows up in all of our infrared photographs. Now when I was at TI, I had a photograph, a set of time-lapse photographs of the degradation that showed, since this was relatively dislocation-free material that we had access to, all these dark lines began at the perimeter and propagated into the area of the junction from the edge. And these time-lapse photographs I had showed them beginning to form at the edge and then propagating further and further and further into the device. But unfortunately, I left that photograph at TI when I left, and it was put in storage and then finally destroyed, and nobody knows where it is now. Dark line defects, as far as we know, are planes of semi-insulating material. The defects, when they form, compensate the donors and acceptors and pin the Fermi level near the center of the gap. And they seem to be planes perpendicular to the plane of the junction. And these dark lines behave like extensions of the diode perimeter, the diode surface that propagate into the emitting area of the diode. Now, these dark lines result in an increase in the depletion layer recombination. It's not minority carrier recombination. Recombination in the depletion region that gives rise to 2 kT current. Now it's usually called NKT current, and N can be any value between 2 and 1, but in the gallium arsenide devices with dark line defects, it's almost invariably 2, which is as high as it can go. And as I said before, the material between the dark lines is unchanged. Now this LED degradation led me to develop Biard's law of light emitters. Everything that emits light contains a fixed number of photons, and how long the light emitter lasts depends on how fast you let the photons out. Now, fortunately, this number of photons is not a universal constant. It's amenable to technology. And we've been improving that number of photons in our devices over the years, and now they're quite good. Honeywell is now one of the leading suppliers of vertical cavity surface emitting laser diodes, and Dr. Villarreal and I collaborate on that project weekly at least. The VCSEL is a laser diode which emits light perpendicular to the top surface of the chip. The VCSEL geometry lends itself to conventional semiconductor manufacturing as opposed to the edge emitters, which you have to cleave in strips and cut in the individual die, mount them on a header, attach the leads before you ever get to test them. The VCSELs you can probe in wafer form and use all the standard technology that's been developed for discrete devices and integrated circuits. This is the VCSEL structure that we use now. There's a proton implant to isolate the diodes that goes down through the p-n junction, the active layer. And the life of the VCSELs, as you can see, has been steadily improving. The last data I have here is for the year 2000, but the cumulative percentage of devices